and tell me the method you use or the answer you can solve, you can get. Let's try question A. Okay, let's try question A. Data from the National Oceanic and Atmospheric Administration indicate that the yearly precipitation in LA is a normal random variable with a mean of 12.08 inches and a standard deviation of 3.1 inches. Assume that the precipitation totals for the next 2 years are independent. Find the probability that the total precipitation during the next 2 years will exceed 25 inches. Can you think about that for a minute? Do you know how to solve the problem? Everybody? Okay, solve the problem. Can you get it? You may forget a little bit about the normal distribution. So let me remind you what you need to use to solve the problem. Okay. First of all, you need to know that if x follows a normal distribution with the mean m, with the two parameters m and sigma squared, then m is the mean value, and sigma squared is the variance factor. Okay. If x1 follows a normal distribution with the mean m1 sigma 1 squared, and x2 follows a normal distribution with the mean m2 and the variance sigma 2 squared. Okay, then x1 plus x2 follows a normal distribution with the mean m1 plus m2 sigma 1 plus sigma 2 squared. Okay, for the variance, sigma 1 squared plus sigma 2 squared. And then x1 minus x2 follows a normal distribution with the mean m1 minus m2, and the value is sigma 1 squared plus sigma 2 squared, not minus. Okay. So if they are independent, of course, if they are independent. So this is what you need to use to solve the problem. Back to our problem. You need to deal with the total precipitation during the next 2 years. So let's say x1 is the precipitation during in the first year, okay, and x2 is the precipitation in the second year. Then question A, you want to deal with the total precipitation during 2 years. So it should be the sum of x1 plus x2. And you want that sum to greater than 25 inches. All right. Do you understand? In order to find this probability, you need to know the distribution of the sum x1 plus x2. On the other hand, x1 follows a normal distribution with the mean 12.08 inch. And the variance is 3.1 square, because 3.1 is the standard deviation. So you get 3.1 square. For x2, you still have the same thing, 12.08 and 3.1 square. Okay, we assume that x1 and x2 are independent. So we can conclude that x1 plus x2 follows a normal distribution with the mean in the sum of the two average values, right? So 12.08 plus 12.08 give you 24.16. And the variance is the sum 3.1 squared plus 3.1 squared. All right. Okay. And what's that? What do you get? We get 19.22, right? So you get 19.22 of the variance. Therefore, I can say that x1 plus x2 minus the mean 24.16 divided by the square root of 19.22. Okay, that follows the standard normal distribution and 0, 1. I denote this one by z. All right, and using this fact, I can get the design probability as follows. It is the probability that x1 plus x2 minus 24.16 divided by the square root of 19.22 greater than 25 minus 24.16 divided by the square root of 19.22. Okay, and that is the probability that z is greater than the right hand side. Okay, and the right hand side we have here is 25 minus 24.16 divided by the square root, and that is 0.1916031. Okay, do you understand? And then you get it by using the integral from 0.1916031 to the infinity 1 over 2 pi e to the power minus t squared over 2 dt. Is there any question, everybody? That clear? Is it okay? And the final answer and the design probability is simply this value. You get 0.4240265. Okay, where a is this number 0.1916. Any questions so far, everyone? Is that all clear? All right. Any questions so far? Good. All right. How about the second question, question B? Can you give it a try and tell me the answer as well? In question B, you want to find the probability that the next year's precipitation will exceed that of the following year by more than 3 inches. Let's say you want to find the probability that x1 is greater than x2 plus by more than 3 inches, right? So plus 3. And this becomes the probability that x1 minus x2 is more than 3. So you need to deal with the distribution of the difference between x1 and x2. If x1 plus x2 follows a normal distribution, then x1 minus x2 also follows the normal distribution. And the mean is the difference of the two mean values. So you get 0 because it is 12.08 minus 12.08. So you get 0. For the variance is the sum of the two variance values. So you get 3.1 squared plus 3.1 squared, and that is 19.22. Okay, and then then you can see that x1 minus x2 minus 0 over the square root of 19.22. Okay, that follows the standard distribution and 0, 1. All right, and you again now you denote this one by z. All right. Then I get the probability that x1 minus x2 minus 0 over the square root of 19.22 greater than 3 minus 0 over the square root of 19.22. Okay. And then you get the probability that z is more than the right hand side. Okay. And that is 0.6842. For 2969. Something like that. And then you can use, again, I can use the integral to get the answer. All right. And that is the integral from 0.684269 to infinity. 1 over square root of 2 pi e to the power minus t squared over 2 dt. Okay. And the answer would be 24.68%. Is that clear? Where B is the right-hand side of this inequality. Is that clear, everybody? Is that all clear? Okay. Okay, now I want to move to the last part of this chapter. Okay. I want to talk about the central limit theorem. Before moving on, I want to remind you this one. So if you remember, you will see that if xi follows Poisson distribution with the parameter lambda I for I from 1 to n, and they are all independent, then the sum of xi also follows a Poisson distribution with the mean lambda is the sum of lambda I. Okay. If xi follows a normal distribution with the mean mi and the variance of I squared, then and they are independent, then the sum of xi is also a normal random variable, and the mean of the sum is the sum of the means, and the variance of the sum is the sum of the variance values. Okay. So we will need this for to move on in the last part of the chapter. Okay. I want to talk about normal. Now I want to talk about normal distribution. You get here. The binomial and Poisson distribution becomes more bell-shaped and symmetric when the mean values increase. You can have a look at the two distributions here. You will see that they are not the same. Obviously, the left distribution is a binomial distribution, and the right distribution, the second distribution, is a Poisson distribution. Okay, and you can have a look at the values here. They are all different, but it is quite interesting that even though they belong to different family of distributions, they belong to different families of distributions. The shape are somehow similar to each other, right? They have bell shape, right? They have bell shape, and they're quite somehow a little bit similar. That's somehow symmetric, right? That's somehow symmetric. Even though the two distributions are not symmetric, but they look quite symmetric. And we want to investigate more on this phenomenon. All right. So if that's true, if the mean values are greater and greater, the binomial distribution and Poisson distributions will reach to a family, a common family of distributions. If that's true, or let's say normal distribution, if you because you already studied that distribution. So that is what we think, right? If that's true, if the mean values are greater and greater, the two distributions will be closer to the normal distribution. The answer is yes. The answer is yes. How come? All right. All right. We're not going to prove the result because we don't have time for that. And we need learn something more than what we just learned to prove it. So I will skip that part. You can look for the proof in some textbook or reference books. Now I want to talk a little bit more about the theorem. Suppose that x1, x2, xn are independent. Okay, they are independent, and we don't need to know their distributions. They are independent, and they have the same mean values, and they have the same variance values. Okay, and we note by Sn the sum of the random variables xi, and the average value x bar is the average value of the h bar is the average value of all the observations. So you can say that h bar is simply the sum divided by n, right? Okay, and then you can find the mean value of the sum, right? The mean value of Sn is simply the sum of the mean values of xk. So you have the sum of n terms, and each term is n. Therefore, the mean of Sn is n times n. For the variance, you see that the variance of the sum Sn is the sum of the variance values xk, and you get sigma squared plus sigma squared n times, and you get n times sigma squared. For the standard deviation, you need to apply the square root of to find the square root of the variance of Sn to get the square root of n sigma squared to get sigma times the square root of n. All right. All right. Now for the mean value of the x bar, you can see that because x bar is Sn over n, the mean of x bar is simply the mean of Sn over n, and that is 1 over n, the mean of Sn, and then you get n, right? For the variance, you can see that the variance of x bar is 1 over n squared. You need to square the factor and time the variance of Sn. The variance of Sn is sigma squared times n, and you divide that by n squared, you will get sigma squared over n. The standard deviation of x bar is simply the square root of the variance to get sigma over the square root of n. Okay. Oh, by the way, you may want to download the file on Weekend Learning for the updated version. Okay. Is there any questions so far, everybody? Is that clear? That's good. May I move on? All right. Now I want to talk about the first result. This is not really the central limit theorem, but this can give you some idea about what we want to do. Okay, so you remember that if xi follows a normal distribution and they are independent, then the sum Sn, sum S will follow a normal distribution. Okay, and because you have m sum of mi and they are all the same, so this is n m and this is the sigma squared n, right? That is for Sn. Then you see that the standard deviation is sigma times the square root of n. And if you standardize the random variable, you will get the standard normal distribution, right? NS follow this normal distribution, and you standardize that Sn minus the mean divided by the standard deviation. You should get the standard normal distribution. Okay. All right. So you can see that if I standardize Sn by comparing this fraction, I should get a standard normal random variable like this. Okay. Similarly, you can see that the standard score corresponding to the x bar also follows the standard normal distribution like this: x bar minus m over sigma over the square root of n should follow the standard number distribution. Okay, this is the exact distribution of the two fractions. Okay. Okay. Well, this is quite interesting and quite useful. We will need this result in the next chapter. Okay, after we finish this part. But this is not the result we need for that we call the central limit theorem. The point is that in this case, we did the assumptions that all the xi follow a normal distribution. Okay, but we don't know the distribution of the xi when we talk about the graph, or the distributions are not really normal. All right, like in the two graphs here, we don't have normal distributions. We only have binomial distributions and Poisson distributions. But it is quite interesting that we can come up with a normal distribution. All right. So my question is, if we don't have normal distributions here, can we still have a similar result? Can we have it? Well, the answer is yes. And that is the contents of one of the most important theorem in probability and statistics. One of the most important probability theorem in probability, the central limit theorem. It says that if xi, if x1, x2, xn are independent and they have the same distribution. So I say that they are IID, means that they are independent and identically distributed. So they are independent and they have the same distribution with the same mean, yes, the same variance, okay, and the variance is finite. But we don't know, we don't really know the distribution of the xi. Okay, then the standard score for xn approximately follows the standard normal distribution. Okay, it does not follow normal distribution. Xn, the standard score, this standard score, this one does not follow a normal distribution. You don't know. Okay, you cannot guarantee that. You cannot guarantee that. But if n is big enough, if you have a lot of observations, all right, then this standard score approximately follows the standard normal distribution. Okay, and you have similar results for the h bar. All right, h bar minus n over sigma over the square root of n. Do you understand? And this is called the central limit theorem. Is that clear, everybody? Is that all clear? Good. Let's consider the following example. A producer of cigarettes claims that the mean nicotine content in its cigarettes is 2.4 milligrams with a standard deviation of 0.2 milligrams. Assuming these figures are correct, approximate the probability that the sample mean of 100 randomly chosen cigarettes is greater than 2.5 milligrams. Can you think about that for a minute? Suppose that x1, x2, xn are content of the secret, the total secret. Okay, the secret. Then they see that they are independent, right? So they are independent, and on the xi follow the same normal distribution. Or not? No, I don't think that that's the same normal distribution, right? They have the same distribution, right? So the mean value of xi is 2.4, right? And the standard deviation of xi is 0.2, but you don't know if xi follows normal distribution or not, or let's say you don't even know the distribution of the xi's. Okay, and then we can so suppose that x bar is the average value x1 plus xn over n. In this case, n is 100 because there are 100 secrets, so you get x 100 over 100. Okay. And then you can find the mean of x bar, which is still 2.4, and the standard deviation of x bar is 0.2 divided by the square root of 100, right? And you get 0.02. Make sense? Is that clear, everybody? Even though we don't know the distribution of x bar, we can see that x bar minus 2.4 divided by 0.02, okay, that approximately follows the standard normal distribution. Is that all clear, everybody? Is that clear? May I move on? Okay. So we know this one, this approximation, approximate distribution. Then we can find the probability that the sample mean, which is x bar, is greater than 2.5. So you want to find the probability that x bar is greater than 2.5, and that is the probability that x bar minus 2.4 over 0.02 greater than 2.5 minus 2.4 over 0.02. Okay, and then I denote this one by z. I should get the probability that z is more than 5. Okay, and that is the integral from 5 to infinity 1 over the square root of 2 pi e minus t squared over 2 dt. Any questions? Okay, all right. Let's have a break. Then after that, I will talk about the applications of the central limit theorem to the case of binomial distribution and Poisson distributions. All right. Okay. All right. Now, we want to talk about some applications of the central limit theorem. Well, in the approximation here, we see that we can get an approximate distribution for the sum or for the average value. If you don't, when you don't know the distribution of the observations, okay. In particular, if you do know the distributions, but they are not normal, well, we can still use the central limit theorem, right? Okay. So I will consider the first case. For the first case, I assume that all the x1, x2, xn, they follow a ability distribution with the parameter p. Okay. It means that xi can take the value 1 or 0 with the corresponding probability p in q. Okay. And then you can find the mean value of xi, which is p. You can also get the variance of xi, which is p times q, right? And then I denote by Sn the sum of xi. So Sn is x1 plus xn. Okay. And then this sum follows. It does not follow normal distribution, but you can standardize that to get something like this: Sn minus the mean np over sigma times square root of n, so you get sigma square root of n times p times q. Okay, and that approximately follows the standard normal distribution, correct? If n is big enough. Is that all clear? All right. On the other hand, if you remember, you will see that suppose that they are all independent.
Em cần xin phải giơ
They are
tay anh.
independent. Then the sum x1 plus xn that follows
Sao lại
a
làm quyền thì bây
binomial
giờ anh hỏi là ai đăng
distribution
ký
with the two
thì em lên đăng
parameters.
ký còn gì
First
nữa ạ?
parameter is n, the second parameter is p. Okay. Is there any questions so
Cho
far?
em làm lại nhé.
Everybody?
Cho đi lại cờ đấy.
Hôm qua em gửi cho nó link thuê bạn trai ở Nhật, xong nó kêu là mọi người còn phải thuê em ý. Em là hay nó dám lên đây nó tìm người yêu có thể họ.
Is that clear?
Có này em mà nói gì phải trừ đi 70%, tin 3%.
Kêu.
Đâu, giơ tay lên.
Rồi đó, em accept rồi đó. Lên đi mọi người.
Từ đừng cho tất cả lên vội. Ok, từ thôi.
Is that clear?
Em vừa cho bạn nào lên.
So if Sn follows a binomial distribution, then you can standardize that to get the standard normal distribution, right? That is what I can say. So simply, this is what you can get.
Sao bạn đi xuống luôn?
Không được, để từ cho bún này lên.
Cho chị bún lên đi.
Bún này khả năng cao là giới thiệu với cả số Việt trì được này.
Em cho chị bún nha.
Thật tin.
So you see that if x is a binomial random variable with the parameters n and p, then x minus np over the square root of npq approximately follows the standard normal distribution when n is big. Okay. How about the continuity correction? What does that mean? Well, suppose that x follows a binomial distribution with the parameter n and p, and you want to find the probability that x is less than 10, for example. Then you come up with the probability that, well, from the result up here, we can say that x minus np divided by the square root of np q, that approximately follows the standard distribution like that. And the probability that x is less than 10 is the probability that x minus np divided by the square root of np cube less than 10 minus np divided by the square root of np cube. Correct? And then you get the probability that z, I denote by z the left-hand side. So this is z. And then you get the probability that z is less than that number, right? That number. I will denote by c. So you get the integral from minus infinity to c, 1 over the square root of 2 pi e minus t squared over 2 dt. Do you understand? Is there any questions, everybody? Okay, good. Now, let's talk about the case. Let's talk about the case when x is less than 10, less than or equal to 10. Then you get less than or equal to 10 here, less than or equal to 10 here, right? But you still have a similar, result here, right? Correct? They are the same, even though these two probabilities are different. Why? Because in general, the probability that x is equal to 10 is not 0, right? It is not 0. X in this case is a binomial random variable, taking the value 0, 1, 2, 3, 4, 5 to n. And x is a discrete random variable, so x, the probability that x is equal to a single number is not 0. That's why you need to find a ways to get a better approximation. So I would say that instead of computing the probability that x is less than or equal to 10, you get the probability that x is less than 10.5. Okay, so you replace 10 less than or equal to 10 by less than 10.5. All right, you have this equation because x is an integer, right? And then you keep doing the same, the same way. You do it in the same way, you get the probability that x minus np divided by the square root of np cube less than 10.5 minus np divided by the square root of np cube. Correct? All right. So you can keep doing that to get the integral from that. From minus infinity to that point, that value, right? And the integrand is the density function 1 over square root of 2 pi e minus t squared over 2 dt. All right. Okay. So this method is called continuity correction. So I will replace the probability that x is less than or equal to k, where k is an integer, by the probability that x is less than k plus 0.5. And for the probability that x is greater than or equals to k, I will replace it by the probability that x is greater than k minus 0.5. Okay. Any questions so far, everybody? Is that all clear? Let's try the following example. Can you think about that for a minute, and then we can go over the problem? Suppose that x1, suppose that x is the number of drivers who wear seatbelt regularly among 500 drivers. Then X follows a binomial distribution with two parameters, 500 and P. P is 75%. Is that clear? Is that all clear, everybody? Okay. And then in question A, you want to find the probability that X is greater than or equals to 360 and less than or equals to 400. Okay. Inclusive means that we have the equal sign over here. This is what you want to compute, and that is the sum probability that X equals K, where K is from 360 to 400. And then you get the sum, K is from 360 to 400. And then you get is that 500 to K, and then 0.75 to K, and then 0.25 to the 500 minus K. Is that clear? Is it all right, you guys? Well, now we want to approximate it using the central limit theorem. Well, x minus, we knew that x minus np. By the way, what's the mean? The mean is np. The mean is np minus the mean over the standard deviation. So the mean in this case is the is n times p, right? And that is 500 times 0.75, and you get 375 for that, right? And the standard deviation, or let's say the variance, you get the square root of the variance, and you get the square root of npq, right? And that is the square root of 500 times 0.75 times 0.25, okay? And you get 93.75. All right. So you get x minus 375 divided by the square root of 93.75 follows approximately follows the standard norm distribution and 0, 1. Is that clear, everybody? Is that all clear? All right. And now you want to find the probability that x is more than 360 and less than or equals to 400. Then I need to use the continuity correction, which is the probability that x is greater than 359.5, less than 400.5. And then you get the probability that x minus 375 divided by the square root of 93 on 75 greater than 359.5 minus 375 divided by the square root of 93.75 less than 400.5 minus 375 divided by the square root of 93.75. Is that clear? All clear, everybody? Is that okay? All clear, right? Okay. Now we can also get a similar result for a Poisson distribution. Suppose that x is a Poisson random variable with a mean lambda, and you know that the value is also lambda, right? Then x minus lambda over the square root of lambda approximately follows the standard normal distribution if lambda is big enough, right? And then you can use that to get to deal with some probabilities, right? And remember to use continuity correction because you want to use a Tina distribution to approximate a discrete distribution, right? And the approximation is good if lambda is greater than or equal to 5. Okay. Let's consider the following example. assume that the number of asbestos particles in a square meter of dust on a surface follows a Poisson distribution with a mean of 1,000. If a square meter of dust is analyzed, what is the probability that 950 of field particles are found? What is the answer? Can you think about that for a minute and tell me the method you used to solve the problem? In order to solve the problem, you can see that X in this case is the number of asbestos particles in a square meter of dust. Then X follows a Poisson distribution with the parameter lambda. In this case, 1,000. And you can see that X minus 1,000 divided by the square root of 1,000. And that approximately follows the standard number distribution with, like that, because in this case, lambda is 1,000 is quite big. And then you want to find the probability that X is less than or equals to 950. Okay. And that is the probability that X is less than 950.5. And then you get the probability that X minus 1,000 divided by the square root of 1,000 less than 950.5 minus 1,000 divided by the square root of 1,000. All right, and then you get the probability that, I suppose that this is Z, then is the probability that Z is less than that number, right? Okay. And then you can use the integrals to get the answer, right? Which is the integral from -infinity to that number, 1 over the square root of 2 pi a minus t squared over 2 dt. Is that all clear, everybody? That's good. All right. The exact value should be in order to get the exact value, you can use the definition of the Poisson distribution to get k is from 0 to 950, and the probability that x equals k should be e to the power 1 minus 1,000 to k over k factorial. Okay. Is there any questions, everybody?
Teacher, why x starts from 0 to 950? When we approximate the Poisson to normal, why doesn't it start from 0 to 950?
Well, but you mean what? You mean that the limit here is 0? Is that what you mean?
No. Cái dòng ở.
I see. I see. So you want to talk about this probability, right?
Yes.
Okay. Yes, that should be okay. If you think about the probability that let's say it's from zeros to, let's say x less than greater than 950. Yeah, that's true. That's true. But you can see that it doesn't change the final result a lot. We can give it a try and we see the difference between them right now. If I don't equal the number 0, then I get, give me a minute for the calculations. I think 950, 950.5 minus 1000, 1000. What you can get here is this number. If you use that approach, okay, 0.0587538. If I only use the other one, and you can check to see that I get almost the same thing. Okay? Because the values here is quite big. And recognize that lambda is big, 950 is big. So yes, you can start with you can start from 0 to 950, but it doesn't change doesn't really change the final answer a lot. Is it okay?
Yes, thank you, teacher.
Yeah. The reason is that the probability that the probability the second term, the probability that actually less than 0 is a very small number. You can check. You can see that it is a very small value. Okay. All right. Now, how about using a Poisson distribution? How about this one? This is the final answer. Is the accurate the exact value. So it is 0.05. You may want to compare them. You want to put down here 0.05783629. That is the exact value, and the approximation values is 0.0587538. Is that clear? Okay, so they are not the same. Obviously, they are not the same. This value is an approximation. That value is the exact value. Okay, they are not the same, but they are close to each other. Okay. Is that clear, everybody? May I move on? Everyone? Okay. All right. So I think we just finished this chapter with the central limit theorem. We have learned the first chapter, the first three chapters. The first chapter includes the concept of probability as a function of events, and then you have the addition rule. You get the product rule to find the probability that the probability of a sum, the probability of a product. You also know how to find the probability of a complement. And then you learn the concept of conditional probability, independence events, decision events, and then you get the concept of mutual independence, pairwise independence, right? And then you learn the total probability formula and the Bayes formula. Okay, so in the second chapter, you learn random variables. Random variables are functions of outcomes. And then you want to learn how to describe the distribution of a random variable. You can use probability mass function for this case. You can use the density function for the continuous case. Okay. Sometimes you don't really have. In general, you don't really have a probability mass function or the density function. That's why you come up with another concept that is the cumulative distribution function. All right. You can go back and forth between the density function, the polynomial function, and the cumulative different function if they are available. And then you can come up with some characteristics. All right. If the probability mass function, the density function, the cumulative distribution function tell you the whole distribution of a random variable, then the characteristics can give you some very important and useful information about a random variable. And then you can get the mean value, right? You get the median. You get the variance, the standard deviation, the interpolation range. All right. And then you get the what else? And then you get the random factors, right? In which you learn John distribution, marginal distribution. Okay, and we only learn discrete random vectors, not continuous random vectors. And then in this chapter, we learn some special distributions, including binomial distribution, Poisson distribution, continuous uniform distributions, exponential distributions, and normal distributions. Okay. The exponential distributions can be used to describe the waiting time between two Poisson events. And a Poisson distribution is used to describe the number of events that you can observe within a period of time or within a region. All right. Binomial distribution is used to describe the number of winning games among several games you played. All right. And we need to suppose that all the games are independent. Okay. And then you learn the normal distribution. Okay. And then you come up with the central limit theorem. All right. We can help you to approximate the distribution of the average value or the sum of some independent random variables with finite variance. All right, so they are everything you need for determinism. All right, and we just finished the first part of the course, including probability. All right, is that all clear? Any questions so far? Do you have any questions about the first part of the course? All right. So if you have no further question about the first part of probability, the first part of the course about probability, and then I will move to the next chapter of confidence interval. Okay.